Okay, so read that first one, the one that has like the tracking a fast jet.
Did you write this one?
Yeah.
Did you make that?
Yeah, I think I did actually. The other one I didn't, obviously. I'm not sure, no, I think I found it somewhere.
Where's the
I
toddler?
don't remember. Just testing.
If it's copyrighted, I'm telling them to sue. I'm kidding.
I don't think I did it. I think it came from somewhere.
So now they're taking their math.
No, it's just like, no, I'm positive of
I don't remember. Okay, do we think we have an idea of what's going on? Notice, I gave you the setup, and then I also gave you the drawing and like the given information part. That's really going to be super key. Don't underestimate that beginning stuff. If you can get that beginning stuff right, I think most of us are going to be able to get the problem right from there. So that's really the key. So we've got like a person.
What's the squiggly?
What is the squiggly? That's like the flight path. I was trying to show it was like a different line. So we've got like a plane.
Looks like he's trying to cross it out.
I know, it's like a clock because the plane is flying over the clouds.
A plane is flying like this, right? So it says we're like a person, so we're like standing, we'll say at the origin. And we're supposed to be tracking that plane with our eyes, so as it goes. So we're like looking like this. So this is where we're looking when the plane is right there. The plane's out here, we're looking like that. If the plane's out further, the angle's going to be even more. So we're looking at the angle between the vertical and wherever we're seeing the plane. So how do you know that? It said, spectator in an air show is trying to follow the jet. You can see them following the jet. The jet follows a straight path, goes a certain speed, and it's 600 feet. So we know vertically that length is 600 feet. We're going to say that's not changing. It's just fixed. It's flying at a level. Okay?
It's close to the ground, but how long?
We're supposed to find the maximum rate of change of the angle between the line of sight and the perpendicular to the flight path. Can we all see how this is the perpendicular to the flight path? The flight path is up there. That's the perpendicular. So they said this angle. Could they have said something about find the rate of change of the angle from the line of sight to the ground?
Yeah.
Yeah, they could have asked us for that angle just as easily. I mean, they picked this one. Okay? So we're supposed to do what? So our question, that's one of our steps that we should definitely do, is they asked us to maximize theta with respect to time, didn't they? So let's just think about this. When do we think that's going to happen? When your head's going like this, when do you think your head is going to be traveling the fastest? When do you think it's going to be going?
At the beginning.
The middle point? The very middle point?
Is it going to be way out here?
No.
No way. It's going to be moving pretty slowly out there because you're only going like this, right? As you get closer, it's got to be somewhere back in here. Is it going to be right at the beginning, though?
No.
Maybe like a little distance out? I'm not sure. But it's got to be somewhere close to the beginning, right? So we should get something like that. Okay. So, yeah, that's what you're doing. Maybe it's like right when you come off like that. I don't know. We'll have a look. Okay. So what kind of conditions did they give us? Okay. Instant info, the 540, what is that? Okay, there's a problem on this one. You guys are listening? Okay. 540 was given in miles per hour. The other thing they gave us was in feet. So we need to be consistent with our units. You need to convert that. So make sure you can convert that miles per hour into feet per second. So I'm going to go miles down here. Feet and miles, how are those related?
5,280 feet per mile.
For 1 mile, okay. So we've got that. That's going to get us to get rid of our miles. How are we going to get rid of hours and change that into seconds?
1 hour, 36.
1 hour is
3,600.
60 squared seconds, right? 60 minutes in an hour, 60 seconds in a minute. Okay, so that number is, I have it for you guys, don't I? What is it?
792.
Feet per second. What matters more than anything else in this is that you label that correctly. What is that? That's how fast the plane's going, but what is it in our picture?
How fast X is changing?
Yeah, like that's how
If
fast
we
this
call
guy's
that
going,
X.
right? We're going to say that's the x-axis and that's the y-axis. So that's how fast x is changing, dx dt. Yeah? And the way we have it drawn is positive, isn't it? Because the plane's going that way. Okay. What else? Did they give us something else? They gave us y is 600 feet. And I think that's it.
You're good to go.
Okay. So, can we come up with a relationship that somehow gives us theta?
Use the tangent possibly.
Yeah. If we look at a triangle like this, right? That triangle, then we've got like what up here?
Opposite.
We've got all those things, right? So we could say the tangent of theta would be an excellent choice. Tangent of theta equals x over y. So I think we've done most of the hard parts of this problem now. At this point we should be able to get what we need. So take a derivative with respect to time, because we're looking at rates, right? We want to respect to time right there, don't we?
Of course.
So we say secant squared of theta
Times d theta dt.
d theta dt, chain rule, equals, how are we going to do that over there?
Quotient rule.
Quotient rule. So we say
Well, y is just
O d high. You got it? That's O, that's the derivative of the top,
minus I.
minus pi d ho over O squared. And now we're solving for what here? What do we
D
want?
theta dt.
We want d theta dt, and it's almost by itself. That's the only thing that's in the way.
Divided by secant squared.
Secant squared. So if we divide by secant squared theta, what's that the same thing as doing?
Multiplying by 1 over secant squared theta.
Yeah, so what? I think this is an easier way to do this. What is secant squared of theta also?
1 over.
So really we can multiply a cosine up to the other side, can't we?
Yes. Or you could just divide by secant squared.
You could. You could. I'm just thinking cosine's a friendlier beast than secant.
Fair enough. Fair enough.
I think you'll see why that is at the end of the problem. So you might leave it alone now, divide by your secant squared, and you'd see at the end that you need to like flip it. Okay. So let's see if we can start plugging stuff in. Can we plug stuff in? I think now is the time finally to use that instant stuff. Remember, you do not use that instant stuff until the end. I don't know. Thank you.
T's usually right than theta.
You do make mistakes.
Plug in 600.
Plug in 600 where?
For y. And
So we've got 600.
plug in your dx dt as well.
We've got 600 here. We've got dx dt is 792 right there, right? Minus, ooh. What else do we need?
dy dt.
We need dy dt and x. What's the problem with that?
We don't have
You guys hear Sam?
That's correct.
dy dt is 0. Why?
It's staying the same height above you.
Is the y changing with respect to time? No, it's staying at that same level. So this was actually 0. It was just kind of sneaky, right? So does it even matter what x was then? Which is good. Why?
Because we are trying to.
How can we find x in this problem? At our instant, what's y? This is the instant triangle. Y is 600. They didn't give us x. Did they give us theta at the instant either?
No.
So we would not have been able to find that, so we lucked out, kind of, right? So anyway,
You left off a cosine squared of theta.
I left off a cosine squared of theta. So you plug this in your calculator. I did that for you. So let's see. I got 1.32 about for that, and then I have a cosine squared of theta thing right there. Weird though, like we don't know theta at the instant. Same issue, right? Like we don't know theta at the instant. So are we like out of luck? In most problems, like you should just get a number right now and be done. You know what I mean? Like sometimes you can go back to your instant picture and like solve for something, but I think we only know 600. There's 2 unknowns. Without more information, I think we're screwed.
So is that the answer?
Well, tell me, do you know any trigonometry?
No. I don't know any trigonometry.
Theta
It's been a long time.
So this has a cosine squared theta term in it. Does that have like a max and min? Is that trapped between something? What's cosine squared theta look like? What's cosine theta look like?
Just
What's cosine squared look like? Right? What's it trapped between?
0
in one.
It's not 2 cosine squared of theta or anything, is it? It's cosine squared of theta. So if we want to make this thing as big as possible, the biggest it's possibly going to get is when,
Do you want to set it to 0?
set what to 0?
Or cosine squared theta? Because that's the derivative and finding maximum.
Yeah, I could set it equal to 0 to find my maximum or minimum. I just thought this was a cool way to think about it. I'm just saying, like, without actually solving this, can't we just think about that and say the highest it possibly gets is, the highest this thing can possibly be is 1. So the answer here is d theta dt equals 1.32 times 1. And what are the units on that? Weird units. Just look at this. Theta is, t is,
It's a second.
okay. This, I think that one of the issues you're having, Paul,
I think
is that the question is, are we really setting this equal to 0? You're not.
if you took the second derivative and set that to 0, then
Weren't we just trying to solve for d theta dt? When you do optimization, yeah, you've got to set the derivative equal to 0. But not in this case. We're just trying to figure out, here's an expression for d theta dt. We plugged in the info they gave us at our instant. This thing was 0. This thing, that's how fast the plane was going. This is how high the plane was. This is how high the plane was. And it tells you d theta dt is doing this at that instant in time.
Well, in this particular case, I think we are maximizing it. It does find the maximum rate of change.
Oh, did it say that too?
to maximize it, you just take the second derivative, right? And then set that to 0.
Let's see. Let me make sure I'm not saying something wrong. Find the maximum rate of change of the angle between the spectator's line of sight and a line perpendicular. So we found the rate of change was like this thing, 1.32 times the cosine of theta. Then we, I guess, did have to think about maximizing that thing. So I guess Paul's right. Like we would have had to take
Second derivative.
another derivative of that expression and set it to 0. Did we do it that way? No, we just thought about how big can this expression possibly be by thinking about the cosine squared curve.
Yeah, you should get the same answer.
You should get the same answer. Should we check?
Yeah, sure.
Do it.
Okay. Let's check. Got enough time. We have one more. Let's see.
So that's just 2 times.
2 cosine theta times negative sine theta, 1.32. Is that it? Is that the derivative of the blue guy? Okay. So we've got cosine theta, sine theta equals 0.
So cosine theta equals 0 and sine theta equals 0. And then you'll get 0 and
0.
Where's cosine equal to 0? That's theta equals pi over 2, yeah? Whereas sine of theta equal to 0? 0. So those are critical points. To check them, we'd have to go, I'm going to call this theta prime, theta double prime. Does that make sense? Because that was a theta prime, wasn't it already? So our critical points are at 0 and pi over 2. Can you guys use your calculator and make sure it's in radian mode and give me some test points? Let's test -1. Pi over 2 is 3.14 over 2.
just put pi over 4.
Or we could just put pi over 4. We could put pi in out there, yeah. So plug those in right here. Let's see what we get. You guys are the first group that actually caught that. We could do it this way too. Let's go. I never even thought of it. I just went straight to thinking about it with trig. So when you plug -1 in, what do you get? It's negative.
I didn't get, what'd you plug in? What'd you plug in for your equation?
This
That
is
one?
this is theta double prime right here, right? This guy.
And then put it in.
I got a positive.
Let's
I did too.
confirm.
I got positive.
Let me see what you've got.
It's probably because I didn't have the.
Yes.
Then it might have made it the opposite of sine instead of.
I won't be able to play with you.
Probably did.
In radians?
Yeah.
It is. It's like that with the max theater. It'll be the night we have the night max. Even the night max. I wish I could.
Let's just go like this.
Coach, I'm sick.
And then we get negative at the end.
Isn't that Thanksgiving break? Huh? Isn't that Thanksgiving break?
Beginning.
You like just like sleep in there and like stay.
Yeah, it's negative.
You set your
What
alarm for
else?
like 5 in the morning. I just cracked my
Yeah.
Who else has positive?
I didn't see anything wrong with spread. All three of us.
So?
have
I
the
wouldn't
same
check
answer.
I'm in radians.
1.20027.
Yeah, I got that.
We all have the same.
Brenna.
I got negative on yours too. Oh, I didn't put a negative one. You didn't put a negative one either. Ha! Ha! Found it. Yes. Okay, so positive. Increasing.
You plugged in 1 instead of -1?
Yeah.
Oh.
And so that's
Okay,
the
pi over
negative
4.
right there.
What's
Negative
pi over
right
4
there.
give
That's
you?
fine.
Negative. Negative.
negative. Yeah.
Okay. And pi?
Zero.
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 Oh, pi gave you 0? Let's pick like
Well,
something else then.
That makes sense because
Yeah, one of these things is 0.
sine of
Try
Try
zero.
3 pi over 4?
Yeah, that's good. Try 3 pi over 4. Yeah, I was worried about that.
Positive.
There you go. Max would be 0.
63.
Which is gives you cosine of theta 0.
Does this confirm what we got the other way?
It does.
But I thought we got 1.32.
Cosine
Why is 0 the answer? That doesn't seem to make sense.
Plug it into that.
Okay, you have to plug it into that. I'm just making sure we're all on the same page. Yes? So we confirmed that this is a maximum using calculus. I like the strategy. Just like we did it with trig, but you have to plug in that value, and cosine of 0 is 1. There you go. Okay, very good.
I like it.
Let's do one more. So read that back one. This one on the other side.
Ryan, read the back one. Yeah, I heard.
Could be small group, Adam.
When we tiny group.
Next year?
Are we gonna be? Are we gonna be in my other Calc class? Or are we gonna have our own next year?
Unless something goes wrong.
I said swear.
Like one of the sides.
No, we should have our own. That's really terrible.
That's one thing that could go wrong.
I wasn't. I couldn't even direct that towards you.
I think you might have been talking about something.
Otherwise, I wouldn't say it around me.
Not as extreme. Somebody
Jump to conclusions.
Exactly.
If someone has to die, I vote Myrna. See, I wasn't even thinking that. I would have said your name if I said that, but no chance that you. She thought I was talking about her, but. Her or Alexa?
Maybe they were just like, you're obviously not
Her
your
or
guy.
Alexa?
Hey, you guys all read this?
Yes. Water tank.
It's gonna be everyone in the front row. Is that ironic that we're all
They give you a different number.
Oh wait, Alexa. I forgot about that. She doesn't want to be cool. I thought we killed her.
We have to
Well, apparently.
Okay, that should be enough time. So it says you've got a water tank. This tank is in the shape of a cone. This is like their favorite type of question to ask lately on the free response. They'll have like two different tanks. Something's flowing in one, out of another one. So this is something we're going to do quite a few times this year. Okay. So I think this tank doesn't have a hole in the bottom. It's like water is pouring into the top, like so. Okay, so we're just filling it up. In other words, they give us a couple pieces of information. What are we supposed to find? Find the rate at which the water is rising. That's like some kind of height with respect to time, isn't it? So that's our question. How do we get a height with respect to time? What did they tell us for our info?
Tank being pumped in the tank at a rate of 2 meters cubed per minute, and base radius of 2 meters and a height, base height of not base radius. Base radius of 2 meters and a height of 4 meters.
Okay.
Starting now. Starting.
So, what is this? The water, that's like what's coming in, right?
Yes.
Well, what is that?
It's a rate.
It's a rate of volume,
Yes.
isn't it? It's how much stuff is going in, that's a volume. Okay, what else? They gave us some dimensions, like Adam said. They said that we want to know when the height is 3 feet, meters. So that's also something for our instant. Did they tell us anything else?
Base radius
They told us like the dimensions
of the cone.
of the cones. They said the base radius is 4? 2. So that's 2. What's 4? The whole height, right? So like this. So that should be enough info to get this. So if we want to figure out dH dt, what do you think like the primary equation is in here? You've got a dH dt, you've got a dV dt.
Volume.
Volume, right? Like that's what's happening to the situation. So it's volume of a cone. So the volume of a cone is.
1/3 pi
Squared it.
Remember, like sphere comes from cone. So if you're having trouble remembering that, like I always start with a cylinder first. That's really easy. Cylinder has a circle on the bottom, which is pi r squared times how high it is. A cone is just a third of that same thing, and a sphere doesn't have a height, it just really has a radius in all directions. So you just put a 4/3 there and you replace this with another r, and that's the thing that has r cubed, because a sphere doesn't really have a height. Does that make sense?
Yeah.
Okay. So anyway, we're going to take the derivative, so dv dt. So I'm going to say, what is that going to be? Right now, how many variables do we have? R and H. Is H constant?
You can't put your rest of the info in there.
So if we took the derivative right now, what would we have to use?
Product rule.
The product rule. So we can do that, it'll definitely work, but I think wouldn't it be easier to like solve for something first? If we want dH dt, wouldn't it be really nice to have another equation that describes how does H relate to R?
I know you're not allowed to do this, but can you just put in 4 for H?
Is the height of this amount of water always 4 as it continues to pour in?
I guess.
No way, right? Good question. So we need somehow to relate H to R. Can we do that? I think that they gave us the dimensions of the cone that'll let us do that. Yeah, we can do like a ratio. It's technically similar triangles. Can you guys see over there? I'll try to color code them. So we've got like a blue triangle that looks like this if we go straight down the middle. And we've also got, like, for the whole cone, the whole thing, you've got a triangle that looks like this. So we know that this is 2 and this is 4. And this is the variable r, and this is the variable h. So doesn't that give us a way to express those if we do a proportion?
H equals 2 or
So can't we go like, I don't know, 4
H
over
equals-
2 equals h over r? You know, however you want to do it. It's just similar triangles. Those triangles are similar, so you can get it that way. This is key. You're going to have to be able to do similar triangles. So if we want to get rid of r, we should solve for r. So this is really 2 equals h over r. So 2r equals h. So r equals height over 2. What that's saying, which should make sense, is no matter where this water level is in there, the radius of that water level is half of the height. Does that look kind of right from my picture? Doesn't it look like that radius is maybe half of the height? I tried to draw the cone about right.
I believe it.
Yeah.
If I drew it right, it should be. Yeah? So we're going to stick this in here and we'll make an easier derivative then. So we've got 1/3 pi h over 2 squared h. So that's 1/3 pi, that's just volume, right?
I do that all the time, Mr. McGee.
H cubed over 4, so we've got volume is pi over 12 h cubed.
Indeed.
Finally, we can take a derivative. I mean, you could have done it at the beginning, but it'd been pain.
Would have been
dv dt then is, what's 3 over 12? 1/4. H squared. dH dt. If you had perhaps forgotten that, well, you should know something's wrong, because we were trying to find that, right? So it should be in there somewhere.
Unless you screwed up something else.
True. I guess you could have lots of errors. Hopefully that's not happening.
Or if
Anyway.
you accidentally solved for,
What?
no, it wouldn't make sense anyway. If you placed H instead of R,
Yeah,
you could have done that. So
that's
you could-
true. But then you'd know what you did wrong and you could go back and fix it.
You could have put in 2R instead of putting in.
So if we go 2 divided by the quantity pi over 4 times 9, we'll get our answer. So what is that going to be? Let's make this precise. Flip. So that's going to be 8 over 9 pi on the bottom. Is that right? Weird. So there's the exact answer. Approximately, we probably want the approximate value. What is it?
Oh,
0.3? Yeah. 0.28, and what are our units?
Meter squared cube.
What is this?
Meters per second.
And what will be the last step that I want you guys to do?
Right.
Write it. So you'd want to say in one sentence, therefore, for the water that's pouring into this cone-shaped tank, we're going to, when the height is 3 feet and the rate going in is 2 meters cubed per minute, the height's going to be changing by 0.28 meters per second. That's how fast it's rising, right? It's rising at 0.28 meters per
Minute.
minute. Okay, so there's another one. I think the book has a couple other examples. We will go back to this and do some more of this later this year, but that should be plenty enough for you guys to do it.